And hi everyone, thank you for coming. Please.
Here we go. Let me introduce you.
Right.
So we can have a small pause between the technical difficulties in the talk, right? So we should all welcome Zi Wang. Thank you very much for coming. She's a senior research scientist at DeepMind. DeepMind not down the street, but DeepMind in Cambridge, Massachusetts. Her research is motivated by intelligent decision-making and focuses currently on understanding and improving the alignment between subjective human judgments and Bayesian beliefs embedded in AI systems. Z has also worked extensively on Bayesian optimization, so I think a bunch of us have read some papers of hers on that recently in a reading group here, and also on active learning, Gaussian processes, and robot learning and planning. She completed her computer science PhD at MIT. And has been awarded many awards. Thank you.
Thank you for the introduction. And yeah, it's a great pleasure to be here. So today, I would love to tell you a bit about our recent exploratory work towards bridging the gap between human and AI beliefs. Okay, let's get started. And please feel free to interrupt me anytime if you have questions, comments, because the goal of this talk is really about getting some feedback on this work and see how people, what people think of it. Okay, so first, let me clarify what I mean by human beliefs. I'll use two examples here. Now, let's imagine a scenario where we're learning the new concept Blicket, and we're learning from examples. And suppose I show you that olives in the martini glass belongs to the concept Blicket, and then I ask you, well, are olives on the tree also a Blicket? Okay, you may have the answer here, but the most common one is that, well, maybe, and I have a certain percentage of sureness that it is a Blicket. Now, suppose that I also tell you that this is also a Blicket, then you might be more certain. Okay, let me move this. You might be more certain that the concept of Blicket is relevant to olives. And this is a kind of epistemic uncertainty, and it means that more data, more certainty. Okay, so now in a different scenario, I ask you the question, is an olive a fruit? Do you think an olive is a fruit? Raise your hand if so. Oh, okay, great. So that's a little different from the statistics cognitive scientists have got in, I believe, 1978. So they've conducted an experiment asking a lot of people, is an olive a fruit, and other questions to understand the fuzziness of concepts or sets. So in their particular case of olives, they realized that about 60% of people think that olives are fruits, and the rest didn't. So now suppose that we've seen all the data, and if I ask you, is an olive a fruit? Well, we might be sure that there's a 60% chance that olives are fruits. And this is a kind of aleatory uncertainty, which denotes the intrinsic randomness of a concept. So in both cases, we're predicting or saying a number between 0 to 1, which is a probability, but their meanings are very different. One is about a level of unsureness, and then the other is about fuzziness or the frequency that resulted in fuzziness. Okay, so beliefs are really important because it impact our decision making. That range from daily activities, like for example, like this morning I need to decide, okay, do I bring an umbrella when I didn't look outside? So, but then when I opened the curtain, I realized, okay, it's a sunny day, then I don't need to do that. And then in our daily life as scientists or engineers, we often design experiments to look for a solution that has the best performance. And well, this is related to Bayesian optimization, where we try to do exploration and exploitation on which configurations of the experiment will give us the best result. And then the decision making also have like a lot of implications for safety critical decision making tasks like medical treatment or policy making. So in these cases, we don't know exactly what kind of outcome there will be given our actions or judgments we make, but we'll still take some actions based on our own weighing of risks and benefits of the outcomes. Okay, so we are developing AI models, and as they become more and more capable, a really natural question is, how do we ensure that AI models can also express their beliefs? Because this has like a huge implication on how do we use them for decision making. And you might know the answer. Any guess? All right, we have a shy audience, but okay, I showed the answer. Well, one potential way of doing that is using Bayesian beliefs. They're quantitative measures of uncertainty, and because like we can use them to predict both aleatory and epistemic uncertainty, it acts as a median for us to understand how a model reason and what their thought process is like. Okay, so the problem that I'm proposing here is the Bayesian belief alignment problem, which says, well, we have humans that have certain level of beliefs, and they're relatively subjective. And then we have like AI models that's also trying to express like their beliefs in terms of probabilities, which are quantitative. Then like, how do we make sure they're aligned so that when like the people and the models are given the same set of evidence or observations, they can have similar judgments and eventually have a similar way of making decisions. And then there's the other side of the story, which is that, well, AI models have seen a huge amount of data that we can probably never do in our entire life. It's possible that they discover something new and interesting. And we would like to align with their belief and get to understand what they have learned to advance our own understanding and just make smarter decisions by ourselves. So, well, next I'll talk about two exploratory work towards the goal of having Bayesian aligned like AI systems. And one is to understand the beliefs of these models, in particular large pre-trained model, or even like any model that we have in machine learning. And then the second is to build models to best align with expert beliefs who are using those models to make decisions. Okay, first, probes. So we developed this approach called Gaussian process probes, which is a new interpretability tool that enables us to probe and measure the beliefs of models. And those are the beliefs that the model have about concepts. So first of all, a little bit about probing. The question we ask here is, which concepts can the model represent? And you can think of probing as a way to build classifiers on top of the representations from the model. So given some observations, we can build a classifier based on features from the model. And then whenever we're given a new stimulus, we pass it through the model, get the representation, and let the probe predict whether this particular stimulus belongs to the concept. So for example, olive is a fruit. So typically, one popular way is to train a linear classifier. And what it gives us is a linear probe where it can predict the probability that the stimulus is a fruit. So that's like one probability. That means, okay, is the stimulus the stimulus is a probe with probability 0.5. So that's like our interpretation of it, but we cannot really distinguish between whether that 0.5 means we have low confidence, or does it mean the concept is intrinsically fuzzy? All right, you can probably tell where I'm going with this. So we developed this method called Gaussian process probes, which builds a Gaussian process classifier on top of the model representations and try to understand models' beliefs on concepts using the predictions from the GP classifier. So well, similar to the typical probe that like people have worked with, it also predicts a probability that a stimulus is a fruit. But at the same time, we also have the component of evaluating the probability density of the prediction. So the first is a concept fuzziness, and then the second is the confidence of, that the probe has. Now, let's get a little bit into the detail. So we're changing from the illustrations to the more like formal way of saying it. Suppose our observations are, it's a data set D, and we have 2 data points in our observations. One has negative label, one has positive label. And then we're given a stimulus X, we pass it to the model, and we get the representation, and we feed it into a Gaussian process probe, a GPP, which is parameterized by theta, and this particular model is conditioned on the data set D. So what it gives us is a classifier prediction, let's call it G of A, and that's a number between 0 to 1. So I'm gonna like avoid using the word probability because it means a lot of things. But here, this particular G of A really means the concept fuzziness. And then we also have another prediction, which is the distribution over the classifier. So that's the GP part, and it describes our confidence in the prediction. So this distribution, like you can see it as a distribution over the hypotheses on the classifier, and that will give us the epistemic uncertainty. All right, so just to visualize what this is, we have some, so we have a GPP, and this is really the middle really tries to visualize what kind of samples this distribution has. So remember that each sample is a classifier, so it's a function. So here, like the XY axis are the 2 dimensions of the vector representation A. And given the observations, as we can see here, let's suppose that they're very close because they're just like 2 different olives. So in this case, we can condition on the observations and get a distribution over the classifiers that are all possible explanations on the fact that we have these 2 observations. And then from there, like we have the distribution over G, we can get the distribution for any X, so any stimulus A, any of the vector representation for the stimulus X, so that's A. So on the right-hand side, these are 2 examples. So the top one is an X that's close to our observations. So that could also be another olive. And in that case, because we have those observations, our distribution for G of A, you can see it as a unimodal distribution that's centered at 0.5. So then there's another case where we have a stimulus X that's very far away from our observations in the representation space. And in that case, it will conform to our prior distribution. So in this case, we have a prior that has like two modes, one at 0, one at 1, which means that we believe for typical cases of classification, the label is either 0 or 1. Okay, so a little bit about the details of GPP. We're gonna go with like a relatively high-level explanation, but I can go into detail if anyone's interested. So the first component is a beta Gaussian process. So in this case, we're assuming that the labels Y has a Bernoulli distribution, and then we put a beta prior on its parameter. And then we use two Gaussian process to approximate the classifier distribution. Let me see if I can move this. And then the other part is the specification for the GP in that two Gaussian processes. We use a cosine kernel over the representations. There's a little bit of twist, but basically it's doing an inner product between the representations. And in fact, the hyperparameters of this GP is very interpretable because they just correspond to beta distributions we can inspect by our eyes. And then it depends on like what kind of prior we think the model has. Like for example, we might choose to have multimodal, or we can choose have like a uniform distribution between 0 to 1. And then the third part are measurements of the Bayesian beliefs. So we have epistemic uncertainty, which we call episteme, but I realize the words can be a little confusing. So let's just think about it as the amount of knowledge the probe has about the concept. And that's evaluated by the negative entropy of G of A. And then we have the aleatory uncertainty, and in order to quantify it, we define it as the expected amount of fuzziness, which is the entropy of Y given G of A. So that's a conditional entropy. And then finally, we have the judge probability, which is what's typically given by a classifier. So it's the output of a classifier. And in our case, it's the expected probability that the stimulus belongs to that concept. So expectation of G of A. Yes?
In terms of the choice of the cosine kernel, was there like a particular motivation for that?
Yes. So imagine like in our pre-trained model, right? So say in the computer vision case, we're pre-training model with the outputs being like classes, right? And for each class, it has a linear, so it's basically a linear transformation from the representation to the label. So that's the way we train it. It means that for this particular distribution of classifiers, we can view it as a Bayesian linear regression problem. So that's why we use a cosine kernel, since it's equivalent to doing like Bayesian linear regression.
Okay, is that like a standard? Is that like a known result? I'm just not
familiar with that. So I actually don't know. I mean, I thought it's pretty natural choice.
Okay.
Because in our pre-training stage, we are describing the classifiers as basically a linear function on top of the vector representation. And if we want to construct a distribution over the classifier that can be built on the representations, then our I thought a natural choice is to also describe it as a linear function. Does it make sense?
As in, so in terms of the representation, is this just the final layer
Yeah, imagine it's an activation, although it could be any layer.
Okay. It's just I was just interested because, like, so my understanding of Gaussian processes, a lot of the work is done by a choice of kernel.
Yes.
That's where a lot of the kind of prior comes from.
Yes.
And so I guess by choosing, so cosine kernel has this relationship to Bayesian linear regression.
Mm-hmm.
So by choosing the cosine kernel, you're saying that the representation that you've put the Gaussian process on has some linear relationship to the label.
Yeah, because that's how the representations are learned.
Is in between the activations that it's a linear layer.
Yeah, that's right. Okay. So that's like what happens in the neural net.
Yeah. Okay. Yeah. That makes sense. Thank you.
Okay, great. Any other questions?
I guess I had a related one. I was just looking at this. Is how much work do you get out of the Gaussian process aspect of this? Right? Because in the earlier slide, you said the sort of starting point was a linear probe, and the linear probe obviously only can tell you just a probability number. You can't decompose that. Mm-hmm. You could go from that to a Bayesian linear regression model or linear classification model as your Bayesian linear probe, and then you can do that sort of decomposition between your output and your uncertainty over the linear probe parameters without moving the GP. So I guess, I mean, I was sort of saving it for later, but it's kind of related, I guess. So I was wondering how much the nonlinearity is important if you were looking at.
But GP can be a Bayesian linear regressor. Okay, fine.
So
that's the
GP to parameterize essentially a Bayesian linear regression model.
Right. So that's doing like the inverse on the kernel instead of the inner product of features.
Sorry, I have one more question. If you're applying this onto a representation that would subsequently go into a nonlinear function, or like nonlinear activation function.
Nonlinear?
Yeah. So say
if your A was halfway down the network.
Yeah, exactly. Mm-hmm. Then what in terms of like what are the implications of using a linear probe, and is it whether it's Bayesian or linear? Like what?
Yeah,
I'd like. Is in there seems for me there's like there seems it's for me like I feel like there's some loss of information.
Yeah, so
but I
think
understand how to express the question.
So the cosine kernel is just like our choice here.
Yeah.
But so that means like whether the concepts can be described by a linear sum over the vector representation, but certainly you can use other kernels, and that will give you a slightly different properties. So the whole goal, basically the end goal is that we are trying to probe what the model is thinking. And we're doing this by asking, okay, can the representation result in a classifier that tells some information about the beliefs? By using different kernels, you'll be asking slightly different question in terms of like what the representation is doing.
Okay, so you're saying, does this representation, in this case, you're saying, does this representation linearly represent the label? Okay. Yeah.
And then there's a distribution over it.
Yeah.
Okay. So this is an example where we probe the Bayesian belief of a model COCA. So that's a text image foundation model. And we take the image embedding from it. In this case, we just feed in the observations for the two cases that we just thought about in the beginning of the talk. So the human judgment part is the 60% probability that an olive is a fruit. And for GPP, its prediction turns out to be quite similar to how like human might judge it. So 57% for the probability, while for the knowledge and fuzziness, they describe the epistemic uncertainty and aleatory uncertainty. So we're quantifying them through the entropy So as you can see, so if only one example is used as the observation, then the knowledge is quantified as 0.49 versus if there are two observations at the left, it's 2.3. And then the same goes for fuzziness. For the two examples where we have fuzzy concept, it's 0.63, while the other is slightly lower. So one interesting thing I thought that would be that actually eventually makes sense to me is the rational judgment of uncertainty. So on the left, we have a framework for distinguishing the two dimensions of uncertainty from the literature of cognitive science and psychology. So their framework is saying, well, if we have a way to quantify knowledge, our judged probability would lie in a particular range, depending on whether the judgments are rational. So the way to look at it is on the very left-hand side, when the knowledge is very small, then we probably shouldn't make a judgment on the probability that something will definitely happen, because that would correspond to superstition and judgment that's made based on no evidence. But as we increase the knowledge, we can gradually converge on the ground truth fuzziness or aleatory uncertainty. And only if we have enough knowledge, we can say for sure what kind of fuzziness there really is for the particular event or concept. So GPP makes a very similar kind of prediction. It also predict like 0.5 when the knowledge is relatively limited versus if it has a lot of knowledge, then it's predicting some numbers between 0 to 1. What's nice about GPP is that we can use its uncertainty predictions, in particular the epistemic uncertainty predictions, to do auto-distribution detection. So I'm not going to go into the details, but we evaluated its performance on some ID or OD detection tasks for Shape3D and ImageNet. And we found that GPP performed quite well and also on par with the best benchmark method. All right, so for this part, it's really about like how to understand the beliefs of AI models through probing. And especially for GPP, I help humans to understand model beliefs by producing a rich measurement of uncertainty. And it can also be used for downstream tasks like OD detection, which is kind of nice. All right, yeah, question?
Simple question. So distribution detection will be based on the epistemic.
Sorry, based on what?
So OD detection would rely on epistemic uncertainty measures.
Yes, yeah, because it's a very natural description of like, am I sure or not? Yeah.
Yeah, I think graphs from sort of psychology literature on human decision making. Did you work with someone who was from that field, or is this something you like looked into yourself?
Oh, so this is a paper that's in 2011, and they have a very detailed discussion because I mean uncertainty judgment and decision making is a very core study in those fields, and also like in philosophy. Like people have been wondering about it for a really long time, and in AI or machine learning, we are basically trying to quantify it and see like how we can use it.
I was going to say, was there any ideas from those works that were novel in machine learning setting and that you've been interested in anticipate?
Yeah, I'm sure there is. So this is one example of how to understand the decomposition. So this is like one particular framework. We haven't really looked very much into the details of other kind of work that also describe how to think about uncertainty. But I think overall, I feel like there are a lot of inspirations we can take from those communities.
I think I have a maybe high-level question about how the probe comes in. So you said, I mean, in the last slide of this section, you showed that then the Gaussian process sort of fit between the features and the labels and has these well-calibrated senses of fuzziness and custody, et cetera. But that's kind of its own model, right? So there was this original deep learning model that has its own level of confidence, whatever it might be, right? So that's not necessarily the same. I mean, that's different than what you get out of the Gaussian process, right? So is this an argument for kind of throwing out the output heads from whatever the deep learning model is and putting a Gaussian process layer there in order to achieve calibration? Or is this, do interpretations from the Gaussian process map back onto an understanding of the original model somehow, or?
Yeah, that's a really good question. And I was, I was kind of going vague about it, but basically the confidence here is what the probe has. And if that's a classifier, then that's the confidence of that classifier. In terms of the original model, it gives us the representation. And in that case, I mean, it's just like one representation. It doesn't really mean what the model is thinking. So, I mean, it has relation to what the model is thinking, but it doesn't really have a notion of uncertainty because that representation is fixed. But for aleatory uncertainty, that's like one way of looking at what the model is actually thinking about the concepts. Actually, I think one interesting thing here that we were realizing, which is not included in the paper we actually wrote, is so imagine like we're throwing a coin. So what we typically know that, okay, there's aleatory uncertainty, there's a frequency, it's probably 0.5 if the weight is equally distributed. Now imagine like we have some aliens or superhuman intelligence who can see all the details of your air resistance or force. So if they have access to all those features, all these like a much richer representation, then to them, that's probably deterministic. So that's the difference between like representation and how like aleatory uncertainty might reflect what they're thinking by basically predicting a number. Yeah.
Sorry. In terms of, so how does this differ to kind of just using like a Bayesian neural net and using the epistemic and aleatoric uncertainty?
Yeah, I think for Bayesian neural net, so maybe it's clear to others, but I tend to think it's almost like a black box.
Yeah.
We can't, it's very, like, it's not very easy to understand what it's doing, except that we're putting some distribution over the weights. But then in this case, like we have a very clear definition, and we're just like probing the representation, which is a fixed vector. So it's like easier to think about because it's much simpler model. But I think like definitely like a very important direction is how to do this for more complex models or more complex probes.
Because it's more similar to deep kernel than Bayesian. So it's more similar to deep kernel learning, I guess, than Bayesian neural networks. Yeah,
this is more like using neural net as a part to construct the kernel.
Right.
Okay, have 20 minutes. I'll go relatively fast. So in the second part, we're concerned with the other direction, which is how to encode the expert beliefs into the model. And the motivation is about Bayesianization, where we might be trying to design an experiment, and the goal is to optimize a black box function. So let's think about like how we might do it as humans or experts who are designing the experiments. So at least for me, I would try to reason about my beliefs about the function or which particular design parameter might have a good effect. And then like I might have like a decision-making strategy so that I can make sequential decisions on which design parameters should I evaluate. So one thing we need to think about is that like when I'm reasoning about my belief, or for any experts, when they're reasoning about the beliefs on functions, where do they come from? So the assumption we have is that they might have some intuitions on what the function look like. So they could be smooth, continuous, and then there has been like quite a bit of work studying the human function learning aspect with GPs. And then the other assumption, which seems natural to me, is that the beliefs are a result from past experiences with similar functions. For example, I might have observed data related to these 3 different functions, and then I might form a belief that there's a high variance region, there's a low value region, or there's a high value region. So pre-training GP, one way to look at it is that we're using pre-training to provide a better interface for users or experts to specify their beliefs on functions. Traditionally, what we would do is to pick a mean and kernel and then specify its hyperparameters. So that will give us a distribution, and ideally we might be able to inspect it and see what's going on. But it's kind of like a black box process. So for us, we are pre-training a GP based on a selection of related tasks. And as we will see later, this will give us better alignment with the ground truth, which is defined by the expert belief, or with a caveat under some assumptions. And then it can also improve the performance of Bayesianization methods if we couple it with the pre-trained GP as the prior. Okay, some details. We're making the assumption that all the functions are IAD samples from an unknown ground truth GP. And the observations, so these are kind of common observations, are perturbed by unknown additive Gaussian noise. And then the approach we take for pre-training is that we will define a KL divergence between the ground truth and the model. And then we can basically approximate it and try to minimize it. Okay, let's look at some visualizations on how this works. We have some observed functions, and we start pre-training like maybe from a distribution that's very off from the observed data. And then we can go through like many steps of optimization. And eventually, we would try to characterize both the scale and the variability so that they match better with the observed data. And so the nice thing about it is that the pre-trained GPs will give us better posterior alignment. What I meant by that is the posterior ideally should capture the range of values for each of the input. Suppose we have an unknown function denoted in orange. We are doing like posterior estimate based on some observations. For pre-trained GP, it's able to capture the range of values for this unknown function in a much better way if we don't have a very good GP as a prior. So I'm gonna go quick on these, but basically GP pre-training can enhance the performance of Bayesian optimization from both the theoretical aspect and the empirical one. So from the theoretical side, we can show that the posterior mean and variance can be bounded by the ground truth posterior mean and variance. And because of that, we can achieve a near zero regret bound. So the simple regret is bounded with high probability, 1 minus delta, and the bound is related to the number of training functions, so the number of observed functions. and the number of base-opt iterations. And the near zero part, so it's not zero, but the difference is controlled by the observation noise, so sigma star. In terms of empirical verification, this is one example. We really wanted to see like how it performs in realistic scenarios of hyperparameter tuning for very large machine learning or especially deep learning models. We collected a data set called PD1, which has like 50,000 hyperparameter evaluations of near SOTA deep learning models on image, text, and protein sequence data sets. So this took quite a bit of time, and it's available on GitHub, so feel free to download and see what you can find. For us, we're using this data set as a benchmark for Bayesian optimization. I'm not going to go into the detail of what this graph means, but basically, using pre-trained GP can give us like at least 3 times more efficiency than the best competing method. So another aspect of this is, what if the search space of base-opt are heterogeneous? Previously, for pre-trained GP, all the domains are the same or roughly the same. So that would give us like one GP that would characterize a distribution of functions in the same domain. But often in the case of hyperparameter tuning or doing experiments, our tuning domains can be very different. We just have collected data on a bunch of them. So for example, one domain might be tuning learning rate or number of neurons. For a neural net, the other might have only tuned learning rate. And then for the third case, maybe we have a different model that we're tuning, like a random forest, and it has like totally different hyperparameters, including decision trees or mean number of samples per leaf. We cannot train one single GP to handle all these domains, but the high-level idea is we can potentially learn a model that maps from the search space descriptions to a domain-specific GP so that we can use it in a new Bayesian optimization problem with a new search space. So I'm gonna maybe skip many of the details, but on a high level, what we're doing is to map from the context of hyperparameters of the GP to its prior, so that when we're deploying this particular model with a new domain, we can get the prior distribution for all of the hyperparameters for the GP itself, and then run Bayesian optimization with the hierarchical Gaussian process. So this is what we call the model pre-training on heterogeneous domains, MPHD. And so we trained on data sets and search spaces with a wide range of data from different domains. The inputs actually vary from 2 to 18 dimensions, and that's the HPOB data set. So we found that MPHD achieves the top method for the heterogeneous domain, and it also have a similar performance to pre-trained GP if we have homogeneous domains. Okay, so this is the other direction, which is more about how we can encode the expert beliefs to the model so that it can make similar judgments and decisions to the experts who are using it. So the way we're doing it is for the expert to select relevant tasks and then use them for pre-training. And we were trying to show that it can enhance the performance of Bayesian optimization and posterior predictions. Okay, so that's the 2 directions we had in order to think about the Bayesian belief alignment problem. GP probes can help us to understand the model beliefs or probe beliefs. And then the pre-trained GPs can help us to encode the expert beliefs on functions. And then we can use like both of the methods for downstream tasks, which is like one way of evaluating how good the alignment is. And there are still a lot of different questions in this particular, for this particular problem of how to align the beliefs in both directions. Like, for example, if we have a much more complex model, like how do we really do it? And then the beliefs of humans are also really complex. We have subjective values and potentially like a very complicated understanding of the world, which constructs a complex system of beliefs in our daily life. And can we like develop AI systems that mimic that or align with the complex human beliefs? So that's still a very much unsolved question. And then like if we have an AI model or if we try to align like humans to the AI model, one big question is how do we even evaluate success? So in our case, we're trying to evaluate with downstream tasks or directly inspect, like eyeball what the beliefs look like for ML models. But we need like more, like a more general way of evaluating it, which are like more convincing. All right, so that's it. And thank you for listening. And I'd also like to thank all my collaborators at Google DeepMind and Harvard and Princeton. All right, and any questions? All right, questions. I think we kind of went through it. Ilya.
Sorry, I joined a bit later on. Can you maybe get us back to the theoretical guarantee, the last year? Like, I just joined there. I'm just interested. This rho t. What is that?
Oh, so it's the max like mutual information between the data and the GPU. Okay. So it's like the typical one. Yeah. It's the typical one in like GPU CB.
Right. Yeah, sounds good. And then you're saying as the number of training functions increases, then we can. Well, the first term goes to 1, right?
So the first term, let me point it. So this first term can go to 0 if we have more and more training functions.
Sure.
And I think one interesting thing is it also depends on the number of base of iterations, because that's the number of observations we have.
Sure. So then the second term, just the square root log 1 over delta, that will still multiply the original theoretical guarantee.
Yes.
Right? Yeah. So you can. So then you basically get the standard guarantee, right? The standard simple metrics.
Yeah, which makes sense, right? Like if we have infinite amount of data, we can learn a good distribution that approaches more and more closely with the ground truth, and that's when we get standard guarantees.
Right. Yeah. Yes. Sounds good. And this observation noise, right? Is it also allowed to go to 0?
Yeah, it does, but typically we probably won't have a 0 noise variance for the observations. Yeah,
and just a final question. So when it comes to these plots where you kind of showed this simple regret, right? So this is the standard simple regret, right? It's not like this inference regret, right? Because when you have noise, it's unclear how to report the points, right? Right. We don't actually get to observe the simple regret, right? With noise, and so these curves are just this sort of noiseless simple regret metric, right?
So this is actually, well, in experiments with real-world data, we can't really access the underlying noiseless observations. So this is with noise. Right.
Sure. You can definitely plot it, but I'm just wondering if you look at how to report a near optimal point, rather than rather than just a simple regret. Like simple regret is, I think, meaningful when you have noiseless observations, right? Because then you actually know the value of the points that you observe. The exact one, right?
So if we don't have the exact one,
yeah,
we would still get, so in the standard setup, if we don't have access to the actual underlying observation on the function, or underlying value on the function, then in that case we would still have a near zero regret because it's controlled by the noise variance.
Sure.
Yeah.
All right, thanks.
Yeah, thank you. Anything else? Okay, I think like we've kind of covered a lot of questions along the way about GPP. So if there's no question, I'm gonna go back to the MPhD part, which is more about heterogeneous domains. Okay, so this is actually a work that I was really excited about because in reality, we don't really have any like we don't always have homogeneous data from the same functions. So a really simple example, let's consider maternal kernel and say that the length scales have log normal priors and the domains, like suppose they are continuous or discrete variables. So one example of the context for length scale could be D and 1, and D denotes the number of dimensions for the input domain, and then 1 is saying, well, if the variable that the length scale corresponds to is continuous, then we set 1. If it's discrete, we set it to 0. Yeah. So in the pre-training phase for MPhD, we actually adopt the first like pre-training schemes we have in the previous method in homogeneous domains. For each domain, we can get the pre-trained length scales, and we also have the context. So in that case, what we can do is to train a model to map from the context to the log normal parameters. And then in deployment, when we have a new domain, suppose it's 2-dimensional, then it can map from the context to the log normal prior, so that we can use it to construct a hierarchical GP and run Bayesian optimization with it. Yeah, so that's the high level idea. And then in our experiments, it's like more complex, but roughly it's about like how do we map from context to a hierarchical GP specification. All right, I think we are about the end of the talk. I'll give you 4 minutes back. Yeah. All right, thank you.